Hey there, in this video I'm going to talk about the limits at infinity, the definition. And the one that I'm going to focus on is the limit as x goes to infinity of f of x is equal to a number. We've done the other one where if you have as x goes to a of f of x is equal to L. So in this definition, right, x is going to infinity, so x is getting larger and larger and larger, but the y values are approaching a number. So this is what gives us a horizontal asymptote. And so this is the definition for a function defined on an interval. Then the limit as x goes to infinity of f of x equals L means that for every epsilon greater than 0, right, this is the any epsilon that's given to us, there is a corresponding number n such that if x is larger than n, then the distance between the y values and our limit is within epsilon. And remember, usually epsilon is a very small number, but now we're saying for a very large n. And so graphically, that's kind of what this means. So we have a function, and the L, the red line or pink line there, is our horizontal asymptote. So as x gets larger and larger and larger, right? So when x is bigger than n, so this is your n. So as you start picking x's that are larger than that, then we start getting close to this, to our horizontal asymptote. So imagine you can move this n, so make it even bigger, right? So if you find another n, you can still find x's above that. And so that's kind of what this is saying. So let's do an example of how do you use this definition to prove a limit. So let's prove that the limit as x goes to infinity of 3x plus 2 over x is equal to 3. And we can look at this limit. The powers are the same, so the limit is going to be the ratio of the coefficients. So I know that the limit should be 3. So now how do we use the definition? So it says for any epsilon, so for every epsilon greater than 0, there is a corresponding n. So now we're going to be looking for the n. So given any epsilon, so our proof, just as we did before with the limit as x goes to a, we're going to start with let epsilon greater than 0 be given. Okay, so you're given an epsilon, but now instead of finding the delta before, we're going to find the n. So we're going to choose the capital N to be something. Right, so we're going to try to find that n. And now our assumption says, so if x is greater than n, then the distance between f of x, right, or y values, and the limit is within epsilon. So these are if-then statements. So if x is greater than n, so we're going to assume that x is greater than n. And so we have to find that n. And then we're going to go, then f of x minus L, which in this case is 3x plus 2 over x minus L, our limit is 3. So normally we will still do the same things as we did before, right? Our f of x is 3x plus 2 over x. Our L in this case is 3. We don't have an a in this case, right? With the previous definition, we were finding let a be knows whatever x was going to, but here we just have infinity. So let's go to our scratch work. So our scratch work is we always start with what we want. So we want the absolute value of f of x minus L to be less than epsilon. So that means we want 3x plus 2 over x minus 3 to be less than epsilon. So this is what we want. So with our scratch work, right, we work backwards to get to our proof. So what are we after? We want to find n. So at some point we want x to be greater than something, and that something is going to be our n. So let's simplify this. Get a common denominator. Right, so common denominator is x, so multiply this by x, top and bottom. So we're going to have the absolute value of 3x plus 2 over x minus 3x over x less than epsilon, put it together. 3x minus 3x, those cancel, so I just have 2 over x is less than epsilon. Now remember here, we're saying that x is going to infinity. So what is the absolute value of x then? X is a positive number, so the absolute value of x is just going to be x. So here I can say this is just 2 over x. We already know 2 is positive, and the absolute value of x, since x is going to infinity, right, that means that x is greater than 0, positive, therefore the absolute value of x is x. And so now we trying to find our x. So kind of everything is positive here, so I can multiply both sides of the inequality and my symbol will stay the same. So what I'm going to say is then 2 is less than x times epsilon, divide by epsilon. And so there is my statement. I have x greater than something. So that is going to be my n. So choose n to equal 2 over epsilon. So let's go back to our proof. So we're going to choose here n to be 2 over epsilon. Now we're assuming that x is greater than n, which is 2 over epsilon. And then just as we did before with the limit as x goes to a proof, we kind of redo our scratch work. So get a common denominator. The 3x are going to cancel, so we're just left with the absolute value of 2 over x. And again, x is going to infinity, which means x is greater than 0, therefore the absolute value of x is x. So I can drop the absolute value. And now there's something that comes out of our scratch work. So I'm going to draw your attention to this portion. We already have here 2 over x. Notice that we have 2 over x here. So this, I can say, is less than epsilon, right? Because of the n that we chose. So because we already know that x is greater than 2 over epsilon. And so that's why we can say that. And you can kind of dissect this a little bit more, right? What does that mean? You can kind of backtrack our scratch work. So x greater than 2 over epsilon, do the same thing. Cross multiply, so I have x epsilon is greater than 2, and which means then that epsilon is greater than 2 over x. This is the same thing as saying 2 over x is less than epsilon, right? Just reverse the inequality. And but this concludes our proof here. This is just my reasoning, but based on our choice of n, this inequality is true. So we have shown that for our particular function and our particular limit, the distance between the y values and the limit is less than epsilon. Right? This was our particular function, our particular limit, and based on our choice of n, we have shown that the distance between the y values and the limit is within epsilon, a very small number. So going back to the picture, right, we have shown that in our case, this is L equals 3, and so we have shown that our function values are within epsilon of our limit, given n equal to, what did we have, 2 over epsilon. Then as long as x is bigger than that, then we are fine. And think about this, right? Like if our epsilon is usually a very small number, so if epsilon is 0.00001, right, then what is 2 over epsilon? N equals 2 over epsilon is going to be 2 over 0.00, how many zeros did I use? Right, and so if you do this is going to be a really big number, right? So 2 divided by 0.00001 will give you a giant number. So x bigger than that. And so as you keep moving that n, right, if I add more zeros to this, that n keeps moving. And so that is what is happening. And so this is an example of a proof as x goes to infinity, and we get a horizontal asymptote. So I hope that this is helpful in doing your own problem, your own example, I should say. Email me if you have any questions.